Hello, we are starting Unit 3, which is exponential and logarithmic functions. 3.1 is going to focus on exponential functions. We'll look at how to evaluate exponential functions as well as shift, reflect, and stretch. So starting with an exponential function. An exponential function, you know it's exponential when you have this form. F of x equals a times b raised to the x. So x is up in the exponent. Your a is not going to be equal to 0. Otherwise, you would just have y equals 0, which is a constant function. B is not going to be equal to 1. And exponential, we're going to be looking at when b is greater than 0. So a in that formula is your initial value. So when you're looking for the y-intercept, if you find f of 0, b to the 0 power is 1, and 1 times a is a. So a is going to be your initial value as well as your y-intercept. B represents your base. So in this formula, a is your initial value or your starting point, and b is your base. So let's look at just evaluating exponential functions. If I said f of x equals 3 times 4 to the x power, and I want you to find f of negative 2, what that means is where I see an x, I will plug in a negative 2. Now, it's really important that you do not take 12 to the negative 2 power because that's not following the order of operations. So what you would do instead is this is 3 times, and then you can write this as 1 over 4 to the positive 2 power. So now I have 3 times 1/16, which is equal to 3/16. And that's your solution. All right, so now let's look at f of 1/2. So this will be 3 times 4 to the 1/2 power. And 4 to the 1/2 power is the same thing as 3 times the square root of 4, which is 3 times 2, which equals 6. So I'll highlight both of those, 3/16 and 6. Here's just a reminder that a common mistake is to multiply like this 3 and 4 together. Remember, order of operations tells me exponents before multiplication. Let's look at the next problem. So in the next problem, we are going to look at how to graph exponential functions. So if I have y equals 3 raised to the x, this is going to be considered exponential growth because the base is greater than 1. So while this problem is growth, exponential growth, when the base is 1/3, which means it's a fraction between 0 and 1, then we get exponential decay. So looking at growth, you can take a table to plot these, and we can plug in negative 2. So 3 to the negative 2 is 1 over 3 squared, which is 1/9. 3 to the negative 1 is 1 over 3 to the positive 1, which is 1/3. 3 to the 0, anything to the 0 power is always 1. 3 to the 1 is 3, and 3 to the second is 9. So then you're going to go ahead and plot these on your graph. If you go left 2 and up 1/9, left 1 and up a tiny bit more, 1/3. At 0, we're up 1. This happens to be the initial value or the y-intercept. And notice y, if we did y1 equals 1 times 3 to the x, you can see that in the formula, a is 1, which is this point right here. Write 1 up 3 and write 2 up 9. So you can see that this starts out really slow, and y equals 0 is the asymptote. And then you can see that this moves up rather quickly. This is called exponential growth, where it starts out really slow and then it gets big really fast. So if we look at the exponential decay, and then we'll do the qualities of the graph, if you have y equals 1/3 raised to the x, when you plug in a -2, so y equals 1/3 to the -2 power, did you know that if the exponent is negative, you can flip the fraction and write the exponent positive? So this is the same thing as 3 raised to the +2 power, which is 9. Same thing with 1/3 to the -1. That's going to be the same thing as 3 to the +1. 1/3 to the 0 power is 1. That's your y-intercept. 1/3 to the first power is 1/3, and 1/3 to the second power is, you would square the 1 and square the 3, which is 1/9. So at left 2, you're up at 9, and at left 1, you're up at 3, and at 0, you're at 1, and then at 1, you're up at 1/3, and then at 2, you're at 1/9. So what happens here is we start here and then we drop quickly. So radioactive decay is going to look like this. And then you're going to approach the asymptote of y equals 0. Let's quickly fill in the characteristics of this graph. The domain is all real numbers because we go left to right forever, so -infinity to infinity. The range is going to go from 0 up to infinity. The intercepts is going to be the y-intercept, and we have a y-intercept at 0 up 1. The asymptote is going to be this line right here. So here's your asymptote, and that line is going to be at y equals 0. This graph is considered increasing because from left to right, we're moving up. So left to right, we're moving up. So it's increasing. And yes, this graph is continuous because we can trace our pencil along it and not lift it up. So it is continuous. Exponential decay, the domain again is going to go from -infinity to infinity, which is left to right forever. The range is also going to be 0 up to infinity. The intercept is the same. It's a y-intercept at 0, 1. The asymptote is y equals 0. The graph is not increasing, decreasing. So the graph is decreasing, which means from left to right, this graph is moving downward, so decreasing. And yes, this graph is continuous. So let's talk about end behaviors really fast. If I'm going to arrow up a little bit to, sorry, this isn't on one page, but end behaviors. So over here, this graph, it's the limit as x approaches -infinity. That means as I go left, 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 f of x is equal to 0, because this, as it moves left, is also getting closer and closer and closer to 0. All right, this end behavior would be the limit as x approaches infinity, which means as I go right, 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 f of x is equal to infinity. End behavior over here, the limit as x approaches -infinity. This means as I move left, as I'm going left, 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 what's happening to y? Y is going up, 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 up to infinity. This one, the limit as x approaches positive infinity means as I go right, 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 f of x is moving towards 0. I say it equals 0 because I'm looking at the limit. Now we're going to talk about how the graph shifts, reflects, and stretches. And looking at that, vertical stretch is when that multiplier in front, so this is a, the initial value is greater than 1. Then you're going to get a vertical stretch because it's going to be moving up quicker. If that number is between, the absolute value is between 0 and 1, then we get a vertical shrink, which means it's moving up slower. Reflection over the x-axis, we throw a negative out in front. Reflection over the y-axis, we would put a negative up here in front of the x in the exponent, and that's going to reflect us over y. Horizontal translation is this h up here in the exponent. Vertical translation is you add or subtract a number, which is k, and the asymptote is always going to be y equals k. So whatever you're adding or subtracting, that's going to be your asymptote as well as your vertical translation. So now what I want you to do is push pause on the video and then just go through and graph these and see what patterns you get. What changes? So you would graph the first graph under y1 and the second graph under y2. You can do this on Desmos or you can do it on your graphing calculator. And you're just going to compare what happens from the first graph to the second graph. And so here we went from a doubling to a quadrupling. And so we ended up getting a vertical stretch. So you'll want to go through and do this all on your own and put what the transformation was. So now what we're going to do is shift, reflect, and stretch this exponential function. Before we do that, we want to get it in the right form. So y equals 3. Instead of 1 subtract x, I'm going to write this as negative x plus 1. So all I did was simply change the order, plus 2. Now you're going to want to factor out that negative in the exponent. So this would be y equals 3 raised to, you take out the negative, and now you're left with x subtract 1, and then plus 2. So the horizontal asymptote is always k, and k is the plus 2. So the horizontal asymptote is going to be y equals 2. And if you look at this picture here, here is 2, and you can see that that's going to be the horizontal asymptote. Now let's go through and answer the questions. So we have y equals 3 raised to the x. I guess you would consider that your parent function. And then we're going to see how we move that. By the way, if the base is a 3, it means you have a tripling rate. Now we rewrote it as y equals 3 raised to the negative and then x subtract 1. And then the plus 2. The horizontal translation is going to be up here in the exponent. So this is the horizontal translation. And that means the horizontal translation is going to go opposite of what you think, just like all the other ones. So if it's x subtract 1, it's actually going to move to the right by 1 unit. Now, the negative out in front is going to be the reflect. So this negative here is the reflect. And because the negative is up in the exponent with the x, that's going to be a reflect over the y-axis. So reflect over y-axis. This has a vertical translation of up 2. That's going to be your k. I can put that one in purple. So the plus 2 is your vertical translation. All right, y-intercept. Y-intercept is where does this graph cross the y-axis? So this is going to be f of 0. And so if you take f of 0, basically this would be f of 0 is equal to the opposite of 0 subtract 1, and then you've got plus 2. So 0 subtract 1 is negative 1, and a negative, oh, I forgot the base, my bad, 3 raised to. So 0 subtract 1 is negative 1, and a negative times a negative is a positive. So that would be 3 to the first power plus 2, which equals 5. So f of 0 is equal to 5. That means that when you plug in 0 for x, your y value is 5. So that is your y-intercept, which is right here at 0, 5. Okay, let's look at example 4, and we're going to use a calculator to evaluate the function of f of x equals e raised to the x. So base e, we're going to talk about in a moment, and they want us to evaluate when we have x is -2. So basically, f of -2 is equal to e raised to the -2 power. So we can throw that into our calculator. Without a calculator, this negative, we could write it as 1 over e squared. And then I'm going to use my calculator to evaluate e to the -2, or 1 over e squared. So I am using a TI-84 plus CE calculator. How you find E is you hit second and then you hit LN, which is on the left. This program will give me the key history down below if you're following and you need to write the key history in your notes. It's second LN. And then it will show you red on my calculator to the left. So e raised to, and then I want e raised to the -2. So I'm going to use the negative down by the enter key, plug in 2, and then hit enter. And you'll need to write down for that example 0.135. 0.135. Let's see if I can do that. So 0.135. All right, so the next thing we're going to do is we're going to use our graphing calculator to sketch the graph, and we're looking for f of x equals 2 times e to the 0.24x. All right, and we're going to talk about what e is in just one moment. So we'll go ahead and sketch this. E is representing a natural exponential function with base e. The 2 is the initial value, which means that the 2 is also going to be where I go through here on the y-intercept. If you have some transformations going on up here, left or right, then that will change your initial value, by the way. All right, so if I were to just make a quick table and I were to plug in -1, then this would be 2 times e to the 0.24 times -1. All right. And then if you wanted to plug in 0, you would have 2 times e to the 0.24 times 0. And that one I can just quickly do by hand because 0.24 times 0 is 0. E to the 0 is 1, and 2 times 1 is 2. And that's this point right here. And then if you were to plug in 1, you would have 2 times e to the 0.24 times 1. All right, and you can fill those in. Let's jump back to the graphing calculator. We're going to go to y equals right now, and then let's go ahead and type in that equation. So it's 2, and then you have times, and then you're going to find e under second ln, which is e raised to, and then put in 0.24, and then x, and x is to the right of green alpha. All right, and then if we want to see what this graph looks like, we can do a zoom and then pick 6 for standard. And there's that graph. So I'm going to graph that in my notes. Now you can go to second and then graph, which is table, and it's going to give you some values. So 1 is 2.54, and -1 is 1.57. So 1.57, -1 was 1.57, and this was 2. I think it was 54, wasn't it? 2.54. So at left one, we're up just 1.5. And at right one, we're up 2.5. So this graph, it's still got a asymptote at y equals 0. And it looks something like that, exponential growth graph. So with your graphing calculator, you're going to go to y equals, and you're going to go ahead and under y1, you're going to put in this function right here. And then you're going to switch your table to ask, from auto to ask. And then you can plug these numbers in, and you can see that as n gets larger, 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 the output is going to approach E. So when you plug 1 in, you end up with 2. As you plug in, let me see if I can write that a little better. So when you plug in 1, your output is a 2. When you plug in 10, and again, I just used my calculator to help me with these, I got 2.59594 if I round 3 places. And then when I plugged in 100, I got 2.705 rounded. When I plugged in 1,000, 2.717. When I plugged in 10,000, 2.719. When I plugged in 100,000, 2.71. Actually, this was 8. 2.718 again. When I plugged in 1,000,000, 2.7183. 2.7183. And so as n moves to infinity using this compound interest formula, it's going to approach 2.7183. That decimal looks kind of weird. Fix it. And that is called E, the natural base. When we explore logarithms and we use base E for logarithms, we're going to write that as ln when it's base E, which is considered the natural logarithm. All of the properties of logarithms that exist for bases other than E also exist for natural logarithms. The values of y are approaching 2.7183. This is the approximate value of the transcendental number E. It's another number like pi. It's irrational. It neither repeats nor terminates. So we will do example 7 in class to save us a little bit of time. And we are going to finish up with page 158 in our notes. Here is the compound interest formula. And if we were in a regular school year, I would tell you to memorize it because you wouldn't be able to use your notes. But you probably could get away this year with just knowing it. The compound interest is when you invest money and then you make interest on your interest the longer you leave your money in. So how often they compound is going to determine how much money you make. The more we compound, the more money we make. So looking at this, if we compound annually, this would be 1 time a year. Semi-annually means that we're going to compound your interest on your interest 2 times a year. Quarterly, 4 times a year. Monthly is 12 times a year. Weekly is 52 times a year. Now, if we compound continuously, that means we're always compounding interest, then you're going to use this formula here where your base is base E, because you can see this formula that we just went over, base E is going to approach this number as we compound going to infinity. So as x is approaching infinity, we end up with base E. Let's do a compound interest. Example 8 is compounding continuously. Let's see. No, example 8 isn't, because this is just the compound continuous formula. Example 8 is compounding weekly. Sorry. So calculate the balance if $3,000 is invested for 10 years at 6% compounded weekly. So what we're going to do is we're going to use the formula right here. Here is the compound interest formula. Amount is how much money we're going to make after the 10 years is over. Principal is what we're investing. So $3,000 is your principal. So we'll fill in the blanks. Time is how long you're investing for. So the time is 10 years. The rate you're going to write as a decimal. So 6% as a decimal is 0.06. And n is the number. So look at n. So your rate's divided by n raised to the nt. N is the number of times you're compounding annually. And because this is weekly, n is going to be 52 times per year. So looking at example number 8, let's go ahead and figure that out. So A is equal to 3,000 times 1 plus 0.06 divided by the number of times you compound annually. And that was going to be 52 raised to the 10 times 52. So n is 52. If you want to write that first, you can. It doesn't matter. I'll change it and put it in order for you. So n is the 52, and 10 is how many total years that we're going to have. This you just plug straight into your calculator, and it's going to give you the amount you would have after 10 years. So we have 3,000, and then you put in parentheses, and then you put in 1 plus, and then green alpha F1 is going to give you a fraction bar. So green alpha and then the y equals key. I really like this fraction bar. I use it quite often. And in the top is the rate, which is 0.06. And in the bottom is the number of times we're compounding. And since it's weekly, we put in 52. We arrow out, we close the parenthesis. Then we put raised to, and then you're going to type in 52 times 10. And then when you hit enter, that's going to be the amount. You're going to round it to the nearest penny. So let's come back to here and let's put in the amount. So we would now have $5,464.47. So your 3,000 has grown to 5,500 about after 10 years because of compound interest. So quickly here, we're almost done. Example 9, the total is $12,000. So I put $12,000 for my principal. That's how much I'm investing, times E. Why did I pick E for my base instead of using the other formula? I picked E because they told me that I was going to compound. Sorry, I'm trying to fix that. They told me that I was going to compound continuously. So because it's compounded continuously, I use base E. Raised to the R, the rate is 0.03. times the time I'm going to invest, which is 4 years. So if you grab your calculator, you are going to need a calculator for this unit. Put in 12,000. E is second ln, which is to the left of the 4, raised to the 0.03 times 4. When I hit enter, I'm going to get the $13,529.96. So that would be my solution. So let's come back here and write our final answer. So our final answer, the amount after 4 years is going to grow to $13,529.96. So the you try you should do in your groups in class. If you're not in class, then you can go ahead and do the you try on your own. You're going to describe the transformations and then give the graph a sketch, and then make sure that you also answer the reflection question. Thanks, everyone.